What's going on, everybody? It's Mr. Gust, and I'm back in the physics classroom. Today, we're talking about the energy basics. Basics into our studies on energy and work. So today, if we look at our equation sheet for our AP Physics 1 equation sheet, we see that this is the equation for change in energy. Okay, so today we're going to discuss this a little bit more, make sense of what this means, and discuss, Jackie, what's happening? Jackie, you want to help?
What?
I need help. You want to help? Guys, Jackie's here. Jackie came in. Jackie left her purse in here, so she had to help come get it. Jackie, you're going to help me with this demonstration, okay? All right, come on. So, do you want to drop it for me?
Yeah.
All right, folks, so you can't really see this here, but Jackie's going to take this bowling ball. This bowling ball is on a string. She's going to hold this string up to my face, and we're going to examine what happens when this bowling ball swings. All right, Jackie, you ready?
Yeah.
Don't remember, just drop. Hang on, go this way because we don't hit a table. She's going to hold it up and touch my chin, and then she's just going to drop it. Ready? Go. And back up. Woo! It almost hits me in the face. All right, Jackie, thank you. Say bye.
Bye.
Bye, Jackie. Okay, so we see that the bowling ball is held at rest up by my face, and then it swings. Jackie let it go, and it swings away, comes to rest on the other side, and swings back. Let's go ahead first and draw a picture of this scenario, and then we'll discuss how this relates to energy and work. So here we go. I've got my initial setup is here, and then after a minute or so, not a minute, but when it's let go, it moves its way back over here, and eventually it swings its way all the way back over here. These are the three different points. I'm going to label these points A. We can label this point A. We can label this point B. We can label this point C over here. Three different cases in this motion. Then it swings back from C to B to A. It goes A, B, C, C, B, A. Back and forth, back and forth, back and forth. And there are really two explanations to this, right? The two explanations that exist are based on what we call systems. So the first explanation that I want to explain to you is going to be a conservation of energy explanation. So let's talk about energy and its conservation. One of the fundamental laws of Newtonian physics is that energy is conserved. It is not created or destroyed in a system in which there are no outside forces acting on it. We've discussed this year quite a bit that the theme of our course is that outside forces cause changes. And so a change in energy is the result of an outside force. That outside force is known as work on the system. So if energy is conserved, there must have not been an outside force on my system. So if I think about this, there's clearly a force that causes this object to speed up, right? Tension is present, but tension is not one of the forces causing it to speed up. It's the weight. It's gravity that pulls the ball down. It's gravity that slows the bowling ball down as it approaches my face. Gravity is the force that causes this thing to speed up and then to slow down. And how do I know gravity causes it to speed up? Well, from A to B, we know that the force of gravity is pointed down and the velocity is pointed down. When they're pointed in the same direction, we call this speeding up. And then from B over to C, the force of gravity is pointed down and the speed is directed upward, or velocity is upward. We call this slowing down. Those are old concepts, but we can still see how there's clearly going to be a speeding up and a slowing down because of the direction of gravity. So what force is acting on this system? It's gravity. If we go back to the idea of conservation, though, there is no outside force. If gravity is not an outside force, we have to think, where is gravity coming from? What must be in my system if gravity is considered part of the system? So our first explanation, our system is going to be the bowling ball and the earth. The earth itself, the mass of the earth and the mass of the bowling ball create the force of gravity. So this is our system. We're going to look at all the energies that are present between the earth and the bowling ball. When I think about this, as the bowling ball is raised above the ground, its position gives it energy. Its position above the earth gives the bowling ball energy, and we call this energy gravitational potential energy. We can abbreviate it as guppy. There is gravitational potential energy at A, okay? As it moves from A to B, is there an outside force? Is there something other than gravity that causes this object to speed up? And the answer is no. The only force that causes this thing to speed up is gravity. And because of that, there's no work done. There is no change. There is a conservation in mechanical energy. As it reaches to point B, it is now moving. We call the energy of movement kinetic energy. So our original gravitational potential energy is now transformed into kinetic energy. And as we move toward point C, that energy is transformed back into gravitational potential energy because the bowling ball, again, rises above the surface of the earth. We are consistently seeing that as it gets further from the earth, there's more gravitational potential energy. And as it gets closer to the earth, there's more kinetic energy. And this ball is going to swing back and forth, back and forth. And because there are no outside forces causing a change in energy, that bowling ball will never reach a height higher than where it started, higher than my chin. If it did, the gravitational potential energy would be greater than where we started, and therefore energy wouldn't have been conserved. There must have been a force causing its height to go higher than the initial height. This is why I'm safe. I know it's not going to hurt me because there is no force. Now, had Jackie taken that bowling ball, lifted it up, and then gave it a little push on its way back to me, it would have hit me in the face because she would have given it some initial energy other than gravitational potential. But because she just dropped it, that bowling ball cannot possibly go higher than where it started because there is no outside force causing it to increase the energy greater than where it started, and it started at the height right below my chin. This is our first explanation. We have a conservation of energy explanation when we are analyzing both the ball and the earth. And the force of gravity is an internal force. It is not an external force. But we can explain this using this equation. We can explain this in a different way. And we can explain this using what is known as the work energy theorem. This means that work is the result of a change in energy, or that work is the result of some force acting on my system. Well, the force that causes this ball to speed up is gravity. And if I call the ball and the earth my system, then gravity is an internal force. But if I call my system, if I want to analyze the ball only, well, now the earth is outside my system. Now the force of gravity is considered an external force. And if that is the case, the ball does not have any energy to begin with. The ball by itself cannot possibly have gravitational potential energy because if I'm just analyzing the ball, there is no height. There's no reference point because the earth is not part of my system. It's not possible to say the ball is X meters above the ground if the ground isn't in my system. It's not part of my system. I can't mention heights or displacements based on that. The ball can't have a height when it's the ball by itself. So initially at point A, there is no energy at all. The ball is not moving. It doesn't have a position relative to itself, so there's no height. These are the two energies we're looking at here. So there's no energy, mechanical energy, stored in my ball at this point. As it moves from point A to point B, there is a force that causes the ball to speed up, and that force is gravity. So what we see is that there is work done by the force of gravity, giving the ball the kinetic energy it has at point B. This is the work energy theorem. There's a force of gravity. It causes a change in energy from 0 joules of energy to whatever my kinetic energy is at point B. However, this is also interesting. At point C, we know again, it stops. It comes to rest as it swings and changes direction. There must be no kinetic energy over there. It's at a height, but again, I can't have a height relative to myself, to the ball itself, so there is no gravitational potential energy. It's not moving. There's no energy at the bowling ball at that point. Well, where did the energy go? If there's a change in energy, there must have been a force to cause that change. What force slowed it down? That would be work, again, done by the force of gravity. This work removed energy from my system. So we can see that work increases energy or it decreases energy here. And when I calculate this out, when I go ahead and solve for the work done, this work term turns out to be positive as I go from point A to point B, because the force and the direction of the motion are in the same direction. And as it goes from point B to point C, that quantity will end up being negative. It will remove energy from my system because the force of gravity is in the opposite direction in which it is moving. This is where FD cosine theta comes into play. If we think about a much more simple scenario, we think about an object that is moving to the right. I'm going to have two different scenarios, but in both cases, the object is moving to the right. If I apply a force on this object right here and move it a certain distance, let's call that distance d, the equation for change in energy or work is equal to force times distance cosine theta, like it says right there. I'm trying to figure out how much of the force is going to speed the object up or change the energy. Well, what is the angle between F and D? Here's my force. Here's my distance. The angle there is 0. So I would say that the work done is equal to F times D times cosine of 0 degrees, which ends up being positive 1. I see work increasing the energy of my system. I apply a force in the same direction I'm moving. I see an increase in energy. This thing will speed up. I have a new explanation for speeding up. Counter to that, if I see this object, work equals FD cosine theta, but in this case, I go ahead and now I'm applying a force opposite the direction of motion, and I apply that force over this distance d. It's moving in this direction, but I'm pulling back on it. That must mean I'm slowing this object down. I end up with work being equal to F times d cosine of 180 degrees. Again, this is positive 1. The cosine of 180 degrees is negative 1. This means my work term will end up negative. This term will be decreasing mechanical energy from my system. Even though work and energy are not vectors, they are scalar quantities. They do not have direction. Work does either increase energy or decrease energy. And it's this funny cosine theta term over here that allows us to determine, if we can't do it conceptually, it allows us to use mathematics to determine, is energy being added to my system like it was in case 1, or is energy being removed from my system, say in case 2. And I see both in my example here. From A to B, energy is clearly being added to my system. The force of gravity is in the same direction it's moving. From B to C, the force of gravity is in the opposite direction I'm moving. I see positive work, additional work, an increasing mechanical energy over here, and I see a decrease in mechanical energy over there. These are the basics of conservation of energy, of work energy theorem. The differences between systems, folks, both of these examples are fine. They are completely accurate. It's just a different approach. The question that pops up is, how do I choose my system? You choose your system, and then you use the appropriate approach to go ahead and explain it or solve for things mathematically. This is your work energy theorem. Here are two ways we can analyze systems based on energy, and here is exactly how we can determine whether or not energy is being added to a system or removed from a system using our mathematical skills. Folks, these are the basics. If you have questions, drop in the comments, ask me in class. Until then, see ya!